Okay, welcome everyone to this next session. In this session, Gabor is going to talk to us about high-performance graph algorithms. So please welcome Gabor.
Thanks for having me. My name is Gabor Szarnas. I'm a researcher based in Budapest, Hungary, and I do all kinds of research on graph processing problems with an emphasis on the performance of graph algorithms. And this is how I came across GraphBLAS. So GraphBLAS is a community effort. This is not my own work, but this is a large informal collaboration that I've happened to join about 1 year ago. So the whole notion of GraphBLAS is that we should try to make graph algorithms high performance, and we should make this accessible to the masses. So what's the fuss about the performance of graph algorithms? Well, it turns out that graph processing is very difficult in terms of performance, and often you take a textbook algorithm, you just naively implement it, run it on a mid-sized data set with a few million nodes, and you find that while the complexity isn't all that high, the actual runtime is very long, and the algorithm that you have implemented is often very slow. There is a great paper by Microsoft Research, which appeared about 3 years ago, and this identified 3 key problems with graph processing algorithms. The first one is the curse of connectedness. This is the inherent rich connected nature of graphs. So by now I think everyone knows that social networks tend to be quite densely connected. So if you start from a person in the social network and then you're looking for 3 hop neighbors, 4 hop neighbors, or 5 hop neighbors, you can basically reach an entire continent with such a short traversal. So you get billions of intermediate results. That's obviously a problem. The other problem is that the modern computer architectures that you can buy were designed to process linear data structures like lists, stacks, or trees at best. But you cannot just go to a shop and buy a processor for graph computations. These are today on the drawing board. There are people working on this, but this is not something that's accessible. So that's obviously a problem, and the third problem that they identified is that these computer architectures are particularly bad at supporting caching and parallelization. So all the typical latency hiding techniques that you can employ when doing dense linear algebra or relational operations just do not work here. So it's very difficult to extract parallelization from graph algorithms. And obviously, we cannot do much with the first aspect. That's just a given of how graphs are structured. That's their inherent value. But we might be able to do something about the other two. And one approach is to try to formulate graph algorithms in a way that they are more digestible by machines. And by this, I mean, let's try to formulate them in linear algebra. There is the widely known data format called the adjacency matrix. This is quite a simple representation. You take a graph of n nodes and you represent it with a matrix which is a square matrix of n rows and n columns. And the semantics of the matrix is that you put a 1 value where there is an edge. For example, here there is an edge from node 7 to node 4, and this is denoted by a 1 value in row 7 and column 4. And you fill the matrix with these 1 values, and the rest is just zeros. And it's kind of immediately obvious that this is a very sparse matrix, so most nodes in a graph are not directly connected to each other. So we can easily compress it into a more concise data structure. So we can just remove a bit of clutter and keep the 1 values. There are many techniques to achieve this. And once we have this data structure, we can use vector and matrix operations to express graph algorithms. For example, if we would like to do a graph traversal, let's say we're interested in traversals originating from node 7, we can start with this vector where the 7th position of the vector contains a 1 value and the rest is just zeros. And if we compute v times a, the adjacency matrix, we will get 1 values in positions 3, 4, and 5, indicating that we could reach these nodes in the graph. And if we do a 2-hop traversals, which is computed with v times a squared, we get values in 1, 3, and 6. And 6 actually has a value of 2, which means that we could find 2 ways to get to node 6 from node 7. So this has kind of tangible semantics. And at this point, you might say that this is all textbook stuff, and indeed it is. There has been like half a century of literature, textbooks, and research papers on how to do linear algebra for graph processing. But unfortunately, there are very few practical implementations. There are some research prototypes, but there aren't that many implementations that, as a regular user, you can just put your hands on and implement some graph algorithms. So the GraphBLAS standard set out to fix this problem. And to understand the etymology of this name, GraphBLAS, we have to traverse back to the late 70s. The late 70s has seen a large increase in scientific computations, but the hardware back then was very heterogeneous. And this was a problem, because if you're a physicist or a chemical engineer and you would like to do some finite element modeling, simulation, or anything else that requires linear algebra, you don't want to spend your time on coming up with a matrix multiplication operation that is efficient on the hardware that you have currently gotten. And if you buy new hardware, you would like to extract the performance of that hardware without rewriting all your underlying matrix multiplication operations. So BLAS, which is an abbreviation of basic linear algebra subprograms, aimed to fix this. And in multiple iterations, it released a standard that captures the essence of dense linear algebraic computations. And this is great because now the concerns of the scientists and engineers who do the numerical applications are separated from those who do the matrix operations and those who design the underlying hardware architecture. So this is a very nice decoupling, and this has essentially revolutionized how scientific computing over dense linear algebra is done. So this is great, but this is not something that we can directly use for graphs. And this has been realized by BLAS developers as well, and there was an extension to the BLAS standard called SparseBLAS in 2001. But it didn't really take up. Maybe the timing was wrong. It wasn't really a successful venture. But 12 years later, something called the GraphBLAS was released, which is an effort to build building blocks for graph algorithms in linear algebra. And it has the very same idea. Let's decouple the concerns of the graph analytical application developers from those who design the underlying hardware and the matrix multiplication operations that serve as the basis of graph computations. And the timing is perfectly right now because we have heterogeneous hardware, we have GPUs, we have FPGAs, and many other ways to do efficient graph computations. One of the cornerstones of these graph computations is the semi-ring-based operation on matrices. So just to recap, matrix multiplication is an operation that can be performed on two matrices provided that their middle dimensions align. So A here is a 4 by 2 matrix and B is a 2 by 3 matrix. And if we are to compute something like the second row and the third column of the resulting matrix C, we essentially compute a dot product from the second row of A and the third column of B. So here we do 2 times 5, 3 times 4, and then we use the addition operator to sum these together, hence giving 22 in that cell. So this is obviously pretty well known. And the idea in GraphBLAS and semi-ring-based graph computation in general is that there is nothing to stop us from taking out this plus operator and the multiplication operator and replacing them with something else, provided that the operation that we are doing still makes sense in some way. So let's try to generalize these matrix multiplication. When I said that it still has to make sense, basically means that it still has to satisfy some basic mathematical properties, and this is captured by the notion of a semi-ring. So a semi-ring is formally this quadruple with a domain, an addition operator, multiplication operator, and an identity element denoted with 0. And we have pretty relaxed requirements. The requirement is that the addition has to form a commutative monoid, which is actually pretty simple. It has to be commutative, associative, and 0 has to act as an identity. And multiplication has to confirm an even more relaxed set of requirements. We only need that it's a closed binary operator. So unlike the mathematical semi-ring, we don't actually require distribution, and we don't require that the multiplication is a monoid as well. So it's pretty easy to satisfy. And everyone in the room already knows many common semirings. For example, the integer arithmetic that we have performed the matrix multiplication on is such a semiring. The real arithmetic is a semiring as well. And if we take more interesting cases, we can have something like a logical semiring when the identity element is false and the addition operator is the logical OR and the multiplication operator is the logical AND. And we have Galois fields, power sets, etc. So it's kind of a rich family of algebraic structures. And the notation is that we put the addition operator first, then a dot, and then the multiplication operator, so we can say like A, OR, and B, and that's the matrix multiplication on that semiring. So how does this work in practice? Well, to stay within the comfortable realm of integer arithmetic, we can compute the number of paths in a graph, as I have shown. So in this example, we start the traversals from node 4 and node 6. And if we do v times a on the integer traditional semiring, and we keep an eye on column 3, we will see that 1 times 1 is 1, 1 times 1 is 1, and then this is aggregated by the addition operator. So we learn that we can traverse from these two nodes to node 3 on 2 paths. So this is nothing new. But how about the case when we're not interested in the number of paths? We would just like to compute reachability. In this case, we can use the Boolean semiring, and this is important because we can save a lot of space by only storing true or false values. Well, only the true values actually, because we can hide the identity element false under the non-1 elements. So if here we compute v times a on this semiring, we learn that true and true is true, true and true is again true, and if we aggregate them with a logical OR operator, then we get true here. So this is a more concise representation, and we lost the information about the number of paths, but it requires a bit less memory. So let's see something more interesting. There is a semiring called the min plus semiring, which is kind of tricky because we take the addition operator and replace it with a minimum operator, and we take the multiplication operator and replace it with the plus, the addition operator. And now the identity element becomes plus infinity. So I've updated the example a bit. Now we have some weights. For example, we know that we have reached node 4 with a cost of 0.5 and node 6 with the cost of 0.6. And if we compute the v min plus a matrix multiplication, we can learn that from node 4 we can go to node 3 with a cost of 0.5 plus 0.4, which is in total 0.9. And from node 6 we can go to node 3 with a cost of 0.6 plus 0.5, which is 1.1 in total. And now these are aggregated by the minimum operator, which selects the cheapest or shortest path from these nodes. So we actually learn that we can go to node 3 with the minimum cost of 0.9. So let's make some good use of this semiring. One of the most essential textbook algorithms is the single source shortest path algorithm. And this can be stated that given from a start node, find the shortest path to every other node in the graph that is reachable from this node. And there is a well-known algorithm, the well-known algorithm, which does repeated relaxation of the edges in each step, and it can be proven to find the shortest path using at most n-1 step for an n-node graph. And the observation is that this relaxation step can be very conveniently captured with this vector matrix multiplication operation that I've just shown. So how does this work? Well, we have to update the definition of the adjacency matrix a bit. So we store, obviously, the weights between the nodes in the matrix, and we also add these imaginary loop edges with zero cost. So we just fill the diagonal with zeros because each node is reachable from itself with a cost of 0. And now we do the multiplications. Let's suppose we start in node 1. So we put a 0 value, like an explicit 0 cost that we are in this node. And each multiplication step will traverse to extend this and relax the edges one by one. So if I remove the clutter, we only get the non-zero values. And the first step will lead us to node 1, 2, and 4. And the next one will lead us to additionally node 3, 5, and 7. Then we will go to node 6. And it's worth keeping an eye on node 3 because that has just been updated from 1.2 to 1.1. And again from 1.1 to 1 because the algorithm finds the actual shortest path, which is 1, 2, 5, 6, and 3. So it found the shortest path from node 1. And now it has reached a fixed point because now it's actually finished the traversal. So this can be summarized with a single slide. So we have this adjacency matrix and we have a 4-line algorithm. There are some other optimizations, like switching between the transposed version of the matrix and the non-transposed version, but that's about it. Okay, let's see another algorithm. This is node-wise triangle count, which is a very important building block in many algorithms, such as computing clustering coefficients or finding communities. The definition of the triangle is actually pretty simple. It's a set of 3 mutually adjacent nodes in the graph. In other words, it's a 3-length cycle or a 3-length closed path in the graph. And here we can see that node 1 is participating in 2 triangles because 1, 2, 4 and 1, 4, 2 form triangles due to the symmetry. So this is actually a very difficult problem to compute. Let's try to solve it in the naive way so that you see why it's actually difficult. So here the idea is that we should just enumerate all 3-length paths and let's check whether one of them closes into itself. And to do this, we compute A times A times A, and then check the elements in the diagonal, because being in the diagonal means that it started from node I and it ended in node I, so it's closed 3-length path. But the problem is that this matrix is no longer sparse. It's actually become very dense and it's very expensive to compute. So that's not really a feasible solution for real-sized problems. One of the optimizations that we can employ is that we replace the second matrix multiplication with an element-wise multiplication that closes these 2-length path wedges into triangles. And then we cannot just conveniently take the diagonal, but we can actually do a row-wise summation to get the number of triangles in each node in the graph. So this looks a bit better because now we could just compute A times A and then do the row-wise summation, but it's still not really ideal because A times A, as you can see, is very dense. So here we can employ the technique called masking, which has been introduced in GraphBLAS. This is an old idea in computer science, and the whole masking is designed to limit the scope of a given operation. So here, instead of computing A times A and doing the element-wise multiplication, we have to just compute the values in the locations that were denoted and colored in gray. So the triangle count algorithm is actually pretty simple. It's just 2 lines of code, and this is actually a high-performance algorithm. You can do bits of tweaking to remove the duplicates, but it's actually pretty easy to implement, and you get high performance. So at this point, you might be asking, how about other algorithms? Well, actually, it turns out that during the last decade, many good folks have been working on it, and they reformulated lots of the classic textbook algorithms in terms of linear algebra. And in all kind of problem categories that you can think of, there is always at least one algorithm that can be captured in linear algebra efficiently. All right, so do I have 1 minute or 5 minutes? Because I thought it's 25.
It's 25 in total.
All right.
So if you use the full 25, then we won't have time for questions. So
okay.
It's up to you.
So basically, then we just speed up. Here is the GraphBLAS C API and the implementations. There is a very elaborate C API, and Sweet Sparks GraphBLAS as the main reference implementation that's actually pretty high performance on CPUs. And for those of you who don't like C programming or just to do productive prototyping, there are Python wrappers on offer. So there are 2 Python wrappers which can be used to concisely capture the algorithms. The ones I've shown are on the right, so it's actually pretty easy to program this. We did a number of benchmarks. We will publish these later this year. There is one with LDVC Graphalytics, which has shown that it can scale up to billions of nodes. And there is another one with the GAP benchmark suite, which is an ongoing effort with collaboration of other graph analytical tools. So it's actually also an ongoing writing, and the paper will be submitted in the next quarter. So this slideshow just goes on and on. So if you're interested, there are 200 plus slides in total. I will put them up to the FOSDEM slide, and I try to formulate all the graph algorithms as concisely as possible. And to sum up, I think this is a really sweet spot in terms of graph computations, because linear algebra is a very powerful abstraction with good expressive power, but also good conciseness. It's not trivial to learn, but it's fairly concrete algebra, so it's actually fairly tangible. And well, the problem is there are only a few graph implementations, GraphBLAS implementations yet, but this seems to be changing. We had many interesting talks related to GraphBLAS in the Graph Dev room yesterday. So overall, I think it's a very promising programming model, and it's a very timely contribution because we are in the age of heterogeneous hardware again. Thank you.
And we do have time for questions.
Which slide? One with a link, sure. So this is it. It's a collection of GraphBLAS related resources.
How easy is it to apply these linear algebra algorithms to temporal graphs?
So the question was how easy it is to apply linear algebraic formulation to temporal graphs. I don't think it has been attempted yet, but probably applying the formalism isn't the problem. The problem is that you have to find some way of versioning this, or some way of representing time, and this is probably subject research. Yes?
Just a curiosity, do you know if there is any documentation about any algorithm to check graph homomorphism?
So graph homomorphism was the question. There are interesting attempts like doing core coding techniques to check graph isomorphism, and checking homomorphism could be done, but I don't think that's the sweet spot for GraphBLAS. But that's also something that's being actively worked on. Yes?
First, thank you for the presentation. It was very good. And second, in your example, you have shown only cases of non-directed graphs. So the matrices in those cases are symmetric.
Yes.
So maybe it's better for performance, and I think that you have experienced that maybe. And the second question was, how do you try to apply that in directed graphs?
So the question was about directed and undirected graphs. This is actually a directed graph instance, so it works pretty well. There isn't much of a difference, so provided that you can transpose the graph, then it works just as well with the directed ones.
So my question is, if I try to onboard with this new organization, do I need to change my data structures compared to the regular class?
The question was whether you need to change your data structures. So the way the whole GraphBLAS API is thought out is that you have opaque data structures, so you trust GraphBLAS to represent your data in the best way that it can, which of course means handing over the responsibility. So it's kind of difficult to take existing data structures and run GraphBLAS on top of that. You usually need an expensive loading step. That said, there were attempts to allow GraphBLAS computations on existing similar data structures. For example, lots of people have data in NumPy or SciPy, and it would be great if they could just use those data structures. So this is something that's on the agenda of the GraphBLAS developers.
Okay, we're out of time. Let's thank the speaker one more time.